Hey thinkers, welcome back to Think Sharp Alley, where every turn leads to a smart solution.
You know, most students think exponents are just about solving 2 to the power 5 or x squared, but in the real world, they are the secret language of scientists, economists, and engineers. Today, we are diving into 3 powerful case studies that will change how you look at the chapter Exponents and Powers. We will be tackling everything from microscopic bacteria and national budgets to quantum computing chips. If you have ever wondered, where am I ever going to use this? This video is for you. Let's get sharp. So let's begin with our first case study. We are in a medical lab and we are looking at bacteria so small you can't see them, but maths can. Now here's a paragraph given. You can read it if you want, but honestly it's just for context. The real focus is on how exponents are being used. In short, what's happening is this. A specific strain of bacteria is growing under ideal conditions. It doubles every hour, and at the same time the researchers are tracking how effective a medicine is in controlling this growth. So all of this is being expressed using exponents. Now let's move to the important part, the question. So the first question, a single bacterium has a length of approximately this meters, and we have to express this measurement in standard form. So now 0 point, we have 3, 4, 5, 6 zeros. And to write this in standard form, the decimal needs to shift how many places? Let's count. So from here, the decimal needs to come after 1. That is the rule of scientific notation, right? So since the decimal is shifting towards the right, our power becomes negative. So how many step negative? 1, 2, 3, 4, 5, 6, 7. So we get 1.2 into 10 to the power minus 7 meter, which is the standard form. Next, we are moving to question 2. The researchers are comparing 2 different bacterial cultures in petri dish. Culture A, mass is given. Culture B, the mass is also given. Which culture has a greater mass? Now, don't let the numbers fool you. Always convert to the same powers of 10 before comparing. Here, I'll convert 10 to the power minus 4 into 10 to the power minus 7. How can I do that? I just need minus 3 over here because minus 4 minus 3 is minus 7. But can I just bring minus 3 just like that? It's maths, not magic after all. So, to balance this out, I need to multiply with 10 to the power 3. So here I multiply 10 to the power 3 into 10 to the power minus 4 minus 3. So minus 3 and plus 3 balances it out. So I get here 10 to the power minus 7, and these two parts, 10 to the power 3 is basically 1000. And when I multiply 1000 with 0.065, I get just 65 because there are 3 zeros, so decimal shift 3 places towards right. So 65 into 10 to the power minus 7. Now that the powers of 10 are same, we can compare just the numbers 65 and 72.1, and clearly 72.1 is greater, which means culture B has greater mass. Now let's have a look at question number 3. There are 2 questions in question number 3. One is OR part. The effectiveness of the medicine over T hours is calculated using the following expression. We need to evaluate it to find the final concentration factor. Now, this looks intimidating, right? But remember our laws of indices, bases like 6, 10, they can be broken down into their prime factors, and that's the secret to simplifying this entire expression. Here at first, we are going to get rid of the negative power. And you know how? By taking the reciprocal of the base. For example, 2 to the power minus 3 is present in the numerator. Once we write this in the denominator, the power becomes positive. Same goes with 10 to the power minus 2. If I write in the numerator, the power becomes positive. Into 6 to the power 0, it becomes just 1. Into 5 to the power 2. And outside we have another power 2. So which means these two powers gets multiplied, and 2 times 2 is 4. And in the denominator we have another 5 to the power 3. Now this 10 can be broken into 5 into 2. So we have 2 into 5 and whole to the power 2 into, so 1 multiplied by any number is that number only, 5 to the power 4, and this 3 being smaller will come up and get subtracted. That is the law of indices. When there is a division, we subtract the powers and divide by 2 to the power 3. Now what happens these two to? It comes over 2 as well as over 5. So we have, and this power being smaller, it will come down and get subtracted. So we have 2 to the power 3 minus 2. And here I have these two power getting added. So 5 to the power 2 plus 4 minus 3 is 1. So final answer over here is 5 to the power 3 by 2 to the power 1. And that's 125 by 2, which is equal to 62.5. So the final concentration factor after T hours would be 62.5. Now the OR part, the growth rate of the bacteria is represented by this equation, where M represents the observation time in hours and we have to find the value of M. So let's have a look at the left hand side. Here we have division, so the powers needs to get subtracted, and since the base are same, so we can subtract the power 3 to the power M minus 2 minus the next power, which is minus 4. So minus of minus makes it plus 4, and which is equal to, now on the right hand side, first of all these two powers, I have just now shown you these two powers gets multiplied on the same base. If there are more than one power, so it gets multiplied. So we have 1 by 3 to the power minus 2 times 4, that's minus 8. Now here we can do some calculation. Minus 2 plus 4 gives me 3 to the power M plus 2, because sign of the greater number, equals to, now I've told you when we have negative power, I just take reciprocal of the base. So it's in the denominator, when it goes in the numerator, the power becomes positive and the denominator is 1, we don't write 1. Now since on both sides bases are same, so powers will be same. So we have M plus 2 is equal to 8, which gives me M equals to 2 goes that side. So 8 minus 2, which is equal to 6. So the value of M over here is 6. Now let's talk big money. We are looking at national budgets where a single decimal error could cost billions. Here the question goes, the government is reviewing the annual budgets for two major departments, the Digital Infrastructure Department and the Science Research Wing. To manage these massive figures efficiently, the Finance Ministry records all expenses using exponents. When comparing or combining budgets, officials must ensure the powers of 10 are matched perfectly. Now this is a classic HOTS question. Here the Science Research Wing spent this much of the total GDP on a specific laser project. We have to express this decimal in standard form. So to convert this number into standard form, we need to make sure that the decimal lies between 1 and 10, right? So we have to shift the decimal point from here to between 4 and 8 here, right? Until we reach a number between 1 and 10 basically. So since we are moving the decimal to the right, the power of 10 will be negative. So 4.801 into 10 to the power minus. Now how much negative? We need to simply count the number of places the decimal moves. So 3 zeros plus 3 more zeros plus 3 more zeros plus 1 more digit 4. So here the decimal shift 10 places. So the number becomes 4.801 into 10 to the power minus 10. Now let's move to the next part. A ministry is comparing the following two emergency funds. Fund A has this much, Fund B has this much money. Find the difference between Fund A and Fund B, and we have to express our answer in standard form. Now to subtract numbers, we must first align the powers of 10. Think of it like making sure the units are same before comparing or subtracting. So we have a term with 10 to the power 12 and we want to express it in terms of 10 to the power 9. So we write 10 to the power 12 as 10 to the power 3 into 10 to the power 9, because 9 plus 3 is 12. right? It comes from the laws of indices. A to the power m into a to the power n equals to a to the power m plus n. Here we are just using it in reverse. Now 10 to the power 3 is 1000. And 1000 when we are multiplying with 0.056, we get 56. Why? Because the decimal shifts 3 places to the right. Now since the powers of 10 are same, we can easily subtract them. Here I am adding 0.0 because the second number has got 1 decimal place. And we are taking 10 to the power 9 common outside. So that gives me 43.6 into 10 to the power 9. But is this answer in standard form? No, because 43 is greater than 10. So we need to shift the decimal point 1 place to the left. It should come between 4 and 3, right? So that it becomes 4.36. And since we are shifting it to the left, and that too by only 1 step, so the power of 10 increases by 1. Remember, when we go towards the right, when we shift the point towards the right, power decreases. And when we shift the point towards the left, power increases. So the final answer is 4.36 into 10 to the power 10. This is how we convert, align, subtract, and finally express the answer in proper standard form. Now let's have a look at the OR part of this question. Now here, remember our rule? We don't allow negative powers. So wherever we have negative powers, we will change their position. That is, if they are in the numerator, they come in the denominator. And if they are in the denominator, they come to the numerator and become positive power. So it's 5 square and 2 to the power minus 4 becomes 2 to the power 4 into 15 to the power 3. And we are left with 625 only, which is actually 5 to the power 4. You can do prime factorization and check it. Now, whichever number is not prime, we are going to break those numbers. For example, 10 and 15. So if I break them up, we are getting this. And this 4 will come over 5 and over 2. And same goes with this 3. And rest of the numbers will stay as it is. Like this. And now we can see 2 to the power 4, 2 to the power 4 gets cancelled. And we are left with all powers of 5. So, in the numerator, we can add up the powers. So, 4 plus 4 is 8. In the denominator also, same base. That means we can add the power up. So, we are getting 3 plus 2. 5 into 3 to the power 3 sits as it is. Now, these two powers having same base. So, these two powers get subtracted. So, 5 to the power 8 minus 5. That's 3 divided by 3 cube was in the denominator. It sits in the denominator. So finally our answer is 125 by 27. Now let's look at the last part of this question. Here we have been given the growth index M of the digital sector is hidden in the following equation, and we have to solve for M. Solving for M is like being a detective. We need the bases on both sides to be exactly the same, right? And over here we have nested powers, single base and so many powers. These two powers gets multiplied. So we have 4 by 7. If we multiply these two, I'm getting minus 6. And rest of the part remains as it is. Now there is a negative power, so we are going to flip the fraction. So if I flip this, the power becomes positive instantly. Into, we have 7 by 4 to the power m minus 1. Now since in the LHS part we have 7 by 4, why keep 4 by 7 over here? Let's flip this power again. So the sign of the power changes. Now here it becomes minus 2. That's alright for now. Now these two bases are same, so the power gets added. So we have 7 by 4 to the power m. 6 minus 1 is plus 5. So m plus 5 and equal to 7 by 4 to the power minus 2. Now since the bases are same on both sides, so that means the power will be same. So m plus 5 is equal to minus 2, and hence I'm getting m equals to plus 5 comes this side, so it becomes minus 5. So minus 2 minus 5 is minus 7. So that's it. Finally, we are going subatomic. Quantum chips move data at the speed of light. So here are the questions of case study 3. A data pulse travels at this second. We have to write the reciprocal of this time in standard form. The reciprocal is just a fancy word for flipping the number. Let us check the decimal places. 3 plus 3, 6, 7, 8, 9. So basically it's 3 by 10 to the power 9. And we have to write the reciprocal of this time. The reciprocal of this time is going to be 10 to the power 9 by 3. Now for our convenience, I'm going to just take one 10 out, and so it becomes 10 to the power 8 by 3. So 10 by 3, it's simple to calculate, so it's 3.33 into 10 to the power 8, which is reciprocal of the time in the standard form. And question number 2 says, two signals are traveling through different cables. Signal A covers some meters, signal beta covers some meters. How many times further does signal alpha travel compared to signal beta? So watch out for the unit trap in this question. We have meters and kilometers. Never compare apples to oranges. So first job is to make the unit same. So to change kilometer to meter, I need to multiply by 10 to the power 3, right? So this immediately becomes 1.5 into 10 to the power minus 5 plus 3, which is equal to minus 2 meter. Now since the units are same, we can now compare how many times further does signal alpha travel compared to signal beta, which means we need to find out the ratio of signal alpha by signal beta. So here 10 to the power minus 2 gets cancelled, and 4.5 divided 1.5 is actually 3. So signal alpha is 3 times faster than signal beta. And in the OR part, the number of transistors n on a circuit is defined by this equation. We have to find the value of n. This is a good question. We just have to compare both sides. When we get same basis, just equate the power and then you get the value of n. So whichever number is non-prime, you have to just break them. So 9 can be written as 3 square, 27 can be written as 3 cube, and 81 can be written as 3 to the power 4, and again we have 27, which is 3 cube. But remember, when we are writing 3 cube, there is already a cube outside, so don't get mixed up. There is a power outside, so you put a bracket and write the power outside. Same goes with the denominator. There is 81, so 81 is basically 3 to the power 4. So you put 81 in bracket and that power of 81 goes outside. Simple. So we got nested powers here. So every nested powers gets multiplied. Like over here I'll get 2n. Here I'm going to get 3 into 3, 9. And down I'll get 4 times 4, 16. Wow. Do you see that? We have all powers of 3. So we will add all of them and we get 3 to the power 2n plus 5 plus 9, and these two powers, there's nothing means 1, will come up and get subtracted. So we have 2n plus 5 plus 9 minus 1 minus 16 equals to, the right hand side remains as it is, 3 to the power 3. Now notice something, that bases are same on both the side. We have 3. So the powers also become same on both the side. So in left hand side, we just need to do a little calculation. So 2n minus 3 is equal to 3. Because 5 plus 9 is 14. 14 minus 1 is 13. 13 minus 16 gives me minus 3. And in the right hand side, we had the power 3. So it comes down. Now minus 3 goes to the right hand side and becomes plus 3. So 2n is equal to 3 plus 3, which is 6. And hence n is equal to 6 divided 2, which is 3. So there are 3 transistors on the circuit. That's it. Third question, the energy efficiency of the chip is given by this expression. We have to find the value of E. This is the final boss of exponent problems. We are dealing with nested fractions and negative powers, so we will take it one bracket at a time. So let's get on with this problem, and we will always start from inside. Now we have 5 to the power minus 1. This bracket remains as it is, and above this minus 1 also remains as it is. So 5 to the power minus 1 is basically 1 by 5 to the power 1. We are not writing it. Divide 4 to the power minus 1 is 1 by 4. Minus, again same thing. This minus 1 remains as it is. And here I have 3 to the power minus 1 means 1 by 3. Divide 4 to the power minus 1 means 1 by 4. Now, we will just solve inside the bracket. So division is there. Remember your fractions. So we take reciprocal, and here I have minus 1. Minus, same thing over here. This is just simple concept of fractions, division of fractions. So now multiplication of fractions. So we have 4 by 5 to the power minus 1 minus here 4 by 3 to the power minus 1. Next we have to take the reciprocal. So 5 by 4 to the power 1, and the next fraction also gets reciprocal. So 3 by 4 to the power 1, which we are not writing. Now the denominators are same, so I'll subtract the numerator. 5 minus 3 is 2 by 4, which is equal to 1 by 2 is the answer.
And there you have it. 3 real-world scenarios where exponents are the hero of the story. Whether it's medicine, finance or tech, the laws of indices are everywhere. Which case study was your favorite? Let me know in the comments below. And if you want to see more HOTS challenges like this, don't forget to hit that subscribe button. Keep practicing, stay curious, and I'll see you in the next one. Bye!